In the previous video, we have discussed about vector space and we have seen what all rules a vector space satisfies. Now here we are discussing about subspace. A subspace is a subset of a vector space and it itself is a vector space. So if this is a vector space, then S is a subset of this vector space. So as it is a subset of this vector space, it will automatically satisfy few of the vector space properties, like it will be commutative, associative, distributive, right? Now few more things it has to satisfy so that it becomes a subspace. It has to satisfy few criterias. Consider there are two vectors u, v and c is a scalar, one real value. First of all, there should be a zero vector in this subset. Second, it should be closed under scalar multiplication. Third, it should be closed under vector addition. So if this subset satisfies this, we can say this subset is a subspace of the vector space. Now consider this xy plane. This is a vector space. This xy plane is a vector space. Consider this subset of this xy plane. Is this a subspace? First we should check if zero vector belongs to this subset or not. So zero vector doesn't belong to this subset, so this is not a subspace. Let's take one more subset. Let's take this subset. Is it a subspace of this xy plane? Now zero vector belongs to this subset. Is it closed under scalar multiplication? Let's take one vector in this subset and scale it. It goes out of this subset. So this is not closed under scalar multiplication. If we multiply this vector with a negative scalar, we'll flip the direction, will go in this direction, and there also we are just moving out of this subset. So this also is not a subspace. Similarly, we can see that if we just take two vectors in this subset, one is this one and one is this one, and let's try adding this two. The addition also is not closed in this subset. So this is not a subspace. Now let's take few trivial scenarios. Is zero vector a subspace? Of course, zero belongs to this subset. Let's check if it is scalar multiplication is closed in this subset or not. So any scalar multiplication of this zero vector is zero itself. So it is, this subset is closed under scalar multiplication. And if we take two zero vector and add them, we get the zero vector only. So it is closed under vector addition as well. Now let's take one line on this xy plane. Is this a subspace? So this is a subset of the xy plane, but does zero vector belong to this subset? No, right? This is the zero vector and this doesn't fall on that line. So this is not a subspace. But let's verify other properties as well. So few vectors on this line are this one, this one, and so on, right? So let's see if this line is closed under scalar multiplication, or Cu belongs to S or not. So if you scale any vector either in positive or negative direction, the scaled vector goes out of that line. So this is not closed under scalar multiplication. Next, check if it is closed under vector addition. Let's take two vector. One is this vector, another one is this vector, and let's add this two. First vector is this one, second one is this one. Let's add this two. The resultant vector doesn't fall on that line. So this is not closed under vector addition as well. This line not going through the origin, this is not a subspace of this xy plane. Now let's take one line that goes through the origin. So the properties we need to check is whether zero vector belongs to this subset or not, whether it is closed under scalar multiplication, whether it is closed under vector addition. So of course the zero vector belongs to this subset. Let's take any two vector on this line. Let's take this is one vector and let's scale it. If we scale it in positive direction or negative direction, the resultant vector also falls on this line only. So this is closed under scalar multiplication. Now let's take one vector in this direction and one more vector either in this direction, or we can take in other direction as well, but let's add this two vector. The resultant added vectors also will fall on this line only. So this line is closed under vector addition as well. So a line going through the origin is a subspace. Now let's take one more example in R2. C is a subset of all xy vectors where x square plus y square equals to 1. So that means this is basically a subset of unit circles. So let's see if it is a subspace or not. If we take any vector in this subset and let's just scale it, it just moves out of this subset, right? So this is not closed under scalar multiplication. Also, if you just take this two vector, one is this vector and another one is this vector, and let's add this two. So the resultant vector also moves out of this subset. So this is not an example of a subspace in R2. Now let's see in this 3D region. Let's take one plane that is going through the origin. Is this a subspace? Of course, the zero vector belongs to this plane, right? So zero vector belongs to this subset. Let's take any vector and scale it in any direction. That also belongs to this subset. So Cu belongs to S, where C is a scalar. Now let's add two vectors, this one and this one. So the resultant vector is this one, that is also on this plane. So this is closed under vector addition as well. So this plane going through the origin is a subspace in this 3D region. If you find this video useful, Please like, subscribe, and let me know about your feedbacks in the comment section.